Hello, so today is November 23rd, Thanksgiving week, and this is model-based imaging, and we finished up the material on Markov chains, so now we're going to do stochastic sampling, stochastic simulation. So what is the issue? Okay, so here's the thing. Stochastic sampling. Okay, so problem. How to generate a sample from some density P of x. And here x might be a member of R, okay, or x might be a member of Rn, okay? So, so the solution, I'll put here the bad solution, is what you do is you compute the cumulative distribution function, right? Right. In undergraduate, did they used to write the integral from something to x of p of x dx? That was like something they do. Do they still do that here? You're an undergraduate here, Colleen, right? I mean, it's horrendous. After class, I'll ask you which classes they did that in, because it's totally wrong, right? It doesn't even make any sense. It's bizarre. Okay, but anyway, we have some legacy textbooks that used to do that. We've probably rewritten them to create new legacy textbooks that do the same thing. But anyway, okay, fine. So this is the cumulative distribution function. And then what you do is this. You say, okay, now this isn't exactly right, but it's close enough. You'll know what I mean. You compute F inverse of, so F is a mapping here from the interval from R to the interval 0, 1, right? That's a cumulative distribution function. F is the, right? So what you do is you create F inverse, which is a mapping from 0, 1 to R, okay? Now, it's not, the problem is F inverse might not exist, but there's a definite, in problem 2 in chapter 2 did this problem, okay? So that's what I mean, okay? And then what I do is I generate, generate a random variable U, which is distributed as uniform on 0, 1, okay? So I can generate a random variable which is uniform on 0, 1, okay? Now, by the way, when I say I hate to get too theoretical, but I will anyway, because it's good for you. When I say a random variable, okay, random variables are neither random nor variables. Okay, that's my new thing. Why? They're functions, okay? So if I say a random variable, you can say to me, I don't know what you're talking about. Construct that random variable, okay? So the onus is on me to construct a random variable if I say a random variable. This could be any random variable with that distribution, okay? So, okay, now the other thing I can mean is, the other thing I mean sort of by analogy is if I write a computer program, I generate a pseudo-random variable, okay, on the computer. Now, you know how to do that, right? If you don't, you just Google pseudo-random number, MATLAB or Python, and it gives you the things, and you do it, right? So you feel comfortable with that. Now, I just want to point out that I can construct a uniform random variable. It's easy. How do I do it? I just do this. I take omega to be equal to the intervals 0 to 1, okay? I take the Borel's, now I'm getting a little bit picky. I take this to be the Borel's sets on 0, 1. Okay. Of course, I never really defined the Borel's, but that's okay. You trust me, right? So what you do is you just take all open and close. You take all open intervals on that thing, or all closed intervals. It doesn't really matter. Say open, and you take the complement of all those intervals, and you take the finite union and intersection of all those sets, and that's the Borel's. Okay. And then you take the measure P to be equal to Lebesgue. How do you spell beg? Something like this, integral. Okay, so, okay, that's your probability space. And then the random variable, x of omega, so the random variable u is a mapping from omega to r, okay, and u of omega equals what? What do you think u of omega equals? At this point, you're completely confused, I'm sure, but it's like so stupidly simple. It's even hard to say. So what is u of omega? By the way, what is omega? Omega is a point in here. So the random variable takes on a value. The random variable is a function, right, from the probability space to R. So in this particular case, what's the obvious choice that makes this the uniform random variable that I want? So this is the probability space. The probability space is of this and P, okay? And this, by the way, is a legitimate probability space because the integral of the measure, or I should say the Lebesgue measure, I guess. The measure of this is 1, so it meets all the conditions, okay? The most important one being that the measure of that is 1, because it's of length 1. If this was a 2, then it wouldn't work. So what do you think the random variable is? By the way, so this is omega, and this is r, and this is the function u. The random variable is a function from omega to r. That's what it is. It's not. There's nothing random about a random variable, and it's not a variable because it's a function. So it's neither random nor a variable, which makes its name especially good. But I think somebody said it. What's u of omega going to be here?
Cardinality of omega.
Excuse me?
The cardinality of omega.
Omega is a number, so it doesn't have a cardinality. Omega is a member of omega, which in this case is the interval 0 to 1. Boy, I've gone off on a good tangent here, but I felt like this is important. You know why? Because in some sense, this is the most fundamental problem people have with stochastic simulation. I can teach all the theory of stochastic simulation, but when I'm done, everybody just goes, huh? They don't quite understand it because they're confused about what the difference is between a random variable and a pseudo-random variable, okay? In a code. Because in the end, the reason you do stochastic simulation is because you want to generate pseudo-random variables in your code, in programs. This is an application-oriented thing. I mean, you can talk about the theory of stochastic simulation in a purely theoretical context, and that's fine. And people can get PhD theses for that sort of thing. And if the government pays you to do it, then you can have fun, okay? But in terms of actually solving anyone's problem, okay, the reason you do this is because you want to write a program that generates random variables to simulate something, right? You have some kind of real-world thing, and you want to simulate it. Like in a material science problem, you might want to generate random grain textures in real materials. Or you might want to simulate a nuclear power plant. Or you might want to simulate a radio receiver, okay? Because radio receivers don't behave in a completely deterministic way. They depend upon the random noise in the system, okay? So if you want to simulate that system, you got to model the randomness of it, okay? So that's why we're doing this. But one of the things people get confused about is this is where the rubber hits the road. And this is why you hear a lot of students talk about realizations of things. They always throw that word in there if they're confused, okay? But the real issue is if you understand what a random variable is, then you won't get confused. And it's a very conceptual thing. The random variable is a mathematical function. It's not random. But you can use it to kind of model things that are random. The actual pseudo-random number you generate in the computer is sort of random in what a human would call like a intuitively random sense. I mean, you can have philosophical arguments. You say, well, it's not random because it's deterministic. You could reproduce it. Well, I could make it dependent on some kind of quantum mechanical thing, and then maybe you'd argue it truly is random. I don't know. But the physical concept of being random is distinct from the mathematical concept, okay? Maybe that's the most important thing to keep in mind. The mathematical concept is formally defined and rigorous. The physical concept is something you and I can talk about, okay? But you can't prove things about the physical world because the physical world just is what it is. You perform experiments and you check to see if the things hold. That's what science is about. But we have these mathematical things, and the reason they're useful is because we can draw an analogy between the physical world and the mathematical world, and then we can prove things about our mathematical world, and we assume they hold in the physical world then, okay? By analogy. But we got to keep straight in our mind what these random variable things are, so we don't get confused. So a random variable is a function. This is a triplet. This is a probability space. But a probability space isn't a random variable. There's no random variable in that probability space. All there are is random events. We can say A is a member of the Borels. Okay, then we can say P of A is some value. So P is a function which maps events, members of this set of Borels, to values in R, okay? And then this thing will be a member of R. Actually, yes, it'll be a member of the interval 0, 1, as a matter of fact, okay? All right, so you got that straight. But it's still, the question is, what's a random variable? What's a random variable, okay? Well, a random variable is a function. It's a function which goes from omega to R. And it has the property so the intuition here is that omega, the probability space, this probability assigns a probability to every event, every subset that can occur on this. And then this is a function you apply to this. And then you can ask the question, well, what's the probability of the events that U falls into some interval? So if you want U to be uniformly distributed, like what function U do you want here? I'll warn you, it's really simple. So here's in the Bayesian distribution of all answers to possible questions. Okay, let's see. One answer is no. That doesn't make any sense in this context, so we can discard it. Yes. Okay, that one doesn't make any sense either, so we'll discard that too. The other one is 0. Can the answer be 0? No, I don't think so, because that would mean the random variable is always 0, right? 1. Could the answer be 1? If it was 1, let's say it's 1, then the random variable would always be 1, right? So is that good? Not really, because if we have that, then the probability that u is equal to 1 is equal to 1, right? And the probability that u is equal to 0 is equal to what? 0. So that's wrong. That's not a correct answer, okay? You see? So it can't, the 2 pi could be an answer, because if you look at the distribution of all answers to all questions that you ever get in an engineering class, 2 pi is like pretty common. But that doesn't make any sense, so we can discard that. E to the x, no, that doesn't work, okay? So let's see, what else could it be here?
The interval 0, 1?
Well, but it has to take on a value. This is a mapping from omega to r, so what comes out of here has to be a number.
Yeah, a real number, some real number.
So what real number? Let's say I make it a, okay? Okay, then the probability that omega equals a is what? By the way, why is the probability? Okay, well, what's the answer, first of all?
1.
It's 1, right? Why? Because what does this mean? You know, it's the simple things in life that are hard, okay? What does this mean? Why do I write that? It means that because it means the probability, it means the probability. Remember, probabilities are only applied to events. So I have to convert it to an event, okay? What is the associated event? The event is the set of omega such that u of omega equals a. That's what it means. That's why whenever I write probabilities, if you notice, I always use curly brackets. I'm actually pretty consistent about that. Whereas the true probability function is a function, so it has regular things. So the reason is this is shorthand notation for that. So what is this equal to? The set of omega such that u of omega equals a. For this case, what's it equal to? It doesn't, u of omega is always a, right?
Yeah.
So it's equal to what? Actually, I'll write this out. I wrote a little bit shorthand here because I was being sloppy. It's really omega, a member of omega, such that u of omega equals a. What's that equal to? It's equal to omega. And what's omega equal to? 0, 1. Okay? So this is equal to the probability of the interval 0, 1, right? And what's the probability of the interval 0, 1? 1. Right? This is basic probability. By the way, actually being able to, you know, the most important thing, I know that, like, as undergraduates, okay, I don't know if they still have this thing, but I'm going to diss it online, so hopefully nobody complains, but they used to have this thing, math counts or something like that, when my kids were young, and they would do these, like, crazy math problems, and they were, like, super hard, and you're, okay, and this is the opposite of that. This is super, super easy. But it's way more important, in my opinion, because it's super abstract and it's super fundamental. Right? Because it really gets to the core of the issue is, what is a random variable? What is it?
Function that maps some outcome to a real number.
Yes, you can think of these omegas as sort of like outcomes, although people avoid using that because they'll often think of the output of the function as an outcome, but I'm totally willing to accept that word, okay? You can think of this as sort of like a random set. This is the core randomness in some sense. And then this is, this is kind of an outcome. Oh yeah. You can have, maybe I don't know. Any way you want to think about it is good, but I think you definitely have it there, okay? So do you see what happens here? So if I set omega equal to A, then the probability that U equals A is 1. So that's not what we need, is it? I can erase all this. So we still haven't answered the question. If we want a uniformly distributed random variable on the interval 0, 1, what does that function need to be equal to? I really hit on something good here, guys. I got to write this down. This should be an exam problem for the future or something like that because it's so simple. Yeah.
1 over all the possible events.
1 over all the possible events. But what's all the possible events?
Okay.
Huh?
Okay.
Excuse me?
In the Barossa.
Oh, this? By 1, okay, so I'm going to write this. 1 over, you mean, now this is a set of sets, right? Do you mean the number of elements in there?
Yeah.
Okay, how many elements are in the Borels? Okay, how many is a single point on the interval? Is the set omega a member of the Borels? I said the Borels are formed by every closed interval. Is this a closed interval? Is this a set a closed interval on those things? Is a single point a closed interval on the set? 0, 1? Yeah, it's a closed interval. So it's a member of the Borels. By the way, what is the measure of this? 0. Right, because the measure is just the Lebesgue measure. So, okay, it's the Riemann integral. Okay, the Riemann integral, okay. Take my word for it, 0, okay? It's 0. It's intuitively the length of the thing, okay? What's the length of a single point? 0, right? Okay. So every point on the line is a member of the Borels, right? So there's at least an uncountably infinite number of points in there. So this is going to be 1 over an uncountable infinity, at least. So that would be 0. So that would be the same as making it 0. And if I make it 0, then what's the distribution? If I make omega 0, then what's the probability distribution of u? This is a u. Of u equals 0. That's what? 1. So is that uniformly distributed on 0, 1? No. See, if I make this any value a, it's not right, because then it will be probability 1, it'll just be a, right? We will, I don't mean this in a nasty way, okay? We're going to spend the rest of this class working on this until we get it, okay? So that might mean you don't want to answer it. That way we can spend the rest of the class on this and not have to do anything else. But this is so important to me, okay, that we have to do this. It's just so important because it's really asking the question, do you understand what a random variable is? Because this is maybe not the simplest. The simplest one would be if I just wanted the random variable. I mean, you know, you can ask the question, is 2 a random variable? Technically speaking, it's not, okay? Technically speaking, it's not. But it almost is a random variable, really, because you could just have the function x of omega equals 2, okay? Then that is a random variable, which is equal to 2 with probability 1. Because it has to be a function to be a random variable. So technically, the number 2 is not a random variable. But if I define the function, which is always equal to 2, then that is a random variable. So you could say, are random variables determinate? Can random variables be equal to constants? The answer is yes. So random variables, well, first of all, random variables are neither random nor are they variables. But in the particular, they don't even have to have any randomness to them. Because I can just, like, you know what, this is almost like typing when you write, you know when you write code, and you say, well, 2 the integer versus 2 the float versus 2 the symbol, you know, versus 2 the ASCII character. Well, all I'm doing is retyping this, essentially. So, okay, so things like, that's why you can ask a question like, oh, it even gets worse than that. You could define A, pick a member of, okay, yeah, I'll pick a member of the Borels, okay, right, such that the probability of A equals 0. First of all, is there such an A? Is it possible to have an A which is non-empty, such that, I'll put here, A is not empty? Is it possible to have a non-empty A which has the property that its probability is 0? Give me an example. Excuse me? I just gave you one, actually, a few minutes ago. Huh?
The singleton.
The singleton. I could take A equal to the omega, right? And then its probability is 0, right? So it's possible to have A's. In fact, there's an infinite number of A's that have that property, right? There's at least a countable infinite number of A's, because every rational number is a point in the interval, right? There's an uncountable number of A's because I could take all points on the reals, okay? But turns out there's a lot more than that. Because there's all kinds of sets that it turns out those are the so-called non-measurable sets, okay? That's what you spend a lot of time on if you take a real analysis course. There's like, you can construct basically a gazillion Googleplex. I mean, it's just unimaginably large numbers of sets that have the property that this is true. Okay, that this is true. Okay, but from an engineering point of view, I guess it doesn't matter. But anyway, okay, so you're good with this, right? So what we do is we say, we define x of omega is equal to omega if, is equal to 2 if omega is a member, is not a member of A, and it's equal to 0 if omega is a member of A. And of course, all these omegas have to be in omega. So now this is a random variable, right? I'll call it x1. Okay, I'm just having too much fun with this. I can't help myself, but it's so important. Okay, and then I can define x2 of omega is equal to 2. And then we'll just make this simpler. We'll say x2 of omega is equal to 2 for all omega, okay? So we have x1 and x2. So you can ask yourself, what's the probability that x1 equals x2?
And A is a non-measurable set?
Excuse me?
Is A a non-measurable set?
Well, there's no non-measurable sets here because this is, I defined A, oh well, I didn't specifically say, but let's say A is equal to omega. It's equal to some value. We'll say A for A in the interval 0, 1. Okay? But it only any A such that the probability of the set is 0, okay? It also could be a countably infinite sum, union, of points in the interval, right? So here, it's equal to 2 if omega is not in A. But if it's in A, it's 0. And here, it's equal to 2 all the time. These are different random variables, by the way. Are these random variables the same? No, because they're different, right? They have 2 different definitions, correct? They're not the same, because if they were the same, they'd have to be equal for all omega, right? But what's the probability that x1 equals x2?
Probability that omega is not A.
It's the probability that omega is not A, right?
Yeah.
So it's the probability of the event omega, of the event A, right? What's the probability of the event A? 0. So the probability, so what's the probability that they're equal?
1.
It's 1. So the random variables are not equal, but they're equal with probability 1. In this case, we say they're almost surely equal. How many people took 600 in here, by the way? Yeah, and you completed it, right? And I'm not picking on the 600 features or course because it's excellent, okay? But it just goes to show, okay, it's a very subtle thing. What is a random variable? So coming back to the original problem I posed, how do you generate a random variable? How do you construct? Not generate is a bad word because it's not a program. This is math. How do you construct a random variable which is uniform on the interval 0 to 1?
It has to depend on the size of omega.
Excuse me?
It has to depend on the size of omega.
Well, omega doesn't have a size. Are you talking about the little omega here?
Yeah.
It's a number. This is a function. I'm going to erase this because now you got that, right? Do you really have it before I erase it? If you have any questions, let's discuss it. Seriously? You good? Okay. But let's come back. This is all about peeling away, let's like Thoreau in Walden Pond. This is like peeling away all the layers of BS, okay, of which are so prevalent in our society these days, and really drilling down to the core ideas, okay? What is a random variable? Okay, so random variable. What is a random variable? A random variable is any, I'm going to say any, technically speaking that's not true, but it's, for all intents and purposes in this class, it's definitely true. It's any mapping from omega to R. It has to be any measurable mapping, but, you know, any mapping you can think of is measurable, okay? And I literally mean that, because you actually can't really think of non-measurable mappings. You can kind of prove their existence, but they don't have any, you can't construct them in any meaningful sense, okay? So literally, any function you can think of, any function you can sort of express in sense, constructively is a random variable, okay? Now, let me just review what we know. If we have u of omega equals 0, well, what's the then what random variable, what's its distribution of that random variable? It's 0 with probability 1, right? So its cumulative distribution function, p of u, is going to, or we'll say f of u, is going to look like y. It's going to look like, and right here, it'll be like that, right? Okay. And if this is 1, then you'll have f of u here. What would its cumulative distribution function look like? You go along here until you got the 1, right? And then 1, you'd be like this, right? Okay. But that's not what we want. We want what cumulative distribution function do we want? We want a cumulative distribution function that looks like this. Correct?
Correct.
How do we get, first of all, is it unique? Is there only one random variable with that distribution? No, obviously not, because we always go IID, right? So we can generate an uncountably, actually, infinite number of random variables all with the same distribution, okay? But I just want, there's an uncountable, at least an uncountably infinite number of random variables with that distribution. I just want one of them. I'm not greedy, okay? Just give me one. So I need a function. You've got to give me a function. And this is the way mathematicians write functions. Omega here, by the way, just to remind you, is the interval 0 to 1, right? So you need to give me a function, which you give me an omega, and I have to give you an output, right? That's what a function is. So what's this thing?
The probability of omega. Probability of omega.
What's the probability of omega? By the probability of omega, you mean the probability of the set omega, right? I assume. What's this?
Yeah.
Oops, doesn't work.
Just give omega.
You get the prize. It's omega. Why? I mean, but this is what it means to be a random variable, okay? Because I say, well, what's the probability that okay, I'll do it like this. The probability that u, say, is less than a, right? For, say, a is in the interval 0, 1, right? By the way, that also happens to be the cumulative distribution function. So that's equal to the probability of the set omega, a member of 0, 1, of u of omega is less than or equal to a, right? That's what it means. Well, if this is what u is, then what does that tell you? Deconvolve this, okay? Well, let's just take this set. I feel like things are shot anyway, so I may as well just use the rest of the board. The set of omega such that u of omega is less than or equal to a, okay? that's equal to the set of omega. The function omega is omega less than or equal to a, right? So what is that?
That's the interval of 0 to
It's the interval from 0 to omega, isn't it?
0 to A.
Huh? Oh, 0 to a, right. Right? So then what's the probability of the interval 0 to a? What is it? It's a. Right? Because this is the probability, we're using the Lebesgue measure. So it's the length of the interval. Correct? Oh gosh, you're thinking, why do people waste their time doing this stuff? You know why they waste their time doing this stuff? Because if they don't understand it, then they just drill gigantic holes in the ground going around in crazy circles that don't make any sense. Okay? So this is A. Well, that's the cumulative distribution, right? Because A is limited to 0, 1. So it works. But it's not just like I went through, I verified this. It's not like I just like pulled this out of the air, okay, and then miraculously it came out. For me, it's obvious. Because the random variable, okay. But I wanted you to torture through it because I felt somehow that would be better. Here's what's happening, okay? Here's the maybe intuition. Imagine that this is omega. I'm going to try to come up. And you have like, this is your circle, okay? And you have 0. This is like 1/2. This is 1/4. This is 3/4. Oh, bear with me. I'm trying, okay? You've seen that TV show Wheel of Fortune or something like that? Or maybe this isn't Spin of Fortune or something. You have like an arrow and you flick it and you go, oh, I know, it's like the game of life where you spin the thing and you go zzz, and you come to some answer. This is the omega space. It's uniformly distributed, okay? So now the idea is the random variable x depends on omega, okay? So if this is equal to omega, what will end up happening is that the x will be uniformly distributed on 0 and 1 to 1, right? If I made x omega squared, I'd get some other distribution, right? I'd get like, so I get that the probability that x is less than or equal to a is equal to the probability that this would be like omega squared is less than or equal to a, right? Which is equal to the probability that omega is less than or equal to the square root of a, right? So this would be equal to the square root of a would be the distribution. That would be the cumulative distribution function. And then the probability density function would end up being the derivative of that. So that would be like 1/2 to 1 over the square root of a or something like that. Is that the derivative? But this is what a random variable is. The idea is you have this single sort of universal distribution on the interval 0, 1. And then you generate everything from that. Omega doesn't have to be just in interval 0, 1. Now, if I wanted to construct a multi-dimensional, if I wanted to check IID random variables, then what I would do is I would make this, like, okay, I don't want to, so do you understand this? So if I wanted to construct IID uniform random variables, so example 2, we did 2 examples today, okay? So we would take omega to be equal to 0, 1 to the n, okay? And then we take the Borel's, we take the sigma algebra to be Borel's on Rn, and then the probability distribution would be Lebesgue measure. I don't know how to spell Lebesgue measure, okay? And that will be for all to see. So now what will happen, and then what will happen is the probability of omega equals 1, because the area in Rn of the unit voxel, okay, is 1 using Lebesgue measure. Okay, so then what I would say is u1, the first random variable of omega, is equal to what? Omega 1, the first component of omega. Because now omega equals omega 1 through omega n, right? And you'd have u n of omega equals omega n. And now you can show those are independent, identically distributed, uniformly distributed, independent, identical, whatever, random variables, okay? So I can, so the problem is, see in my proofs where I start off by saying assume these are uniformly, identically distributed random Gaussian random variables. Like, how can I make such an instruction? I have to be able to prove that they can be constructed. So here's my proof. Now the problem is these are uniform random variables. What if I have Gaussian instead of uniform? Right? Now it comes back to the original problem, which is I have to be able to generate Gaussian random variables. How do I generate a Gaussian random variable? So how do I generate a random variable with some other distribution P of u goes to, say, it's really bad form. I should say f of u. Okay, that's a cumulative distribution function because there may not be any probability distribution. Is equal to probability. Okay, this is a CDF. It's given to me. There is no random variable yet. I'm going to construct it. To construct a random variable, what I do is I compute F inverse. And F inverse now is going to be a mapping from R to the interval to 0, 1. Okay? And now what I do is I make x1 equal to F inverse of u1. Where this is u1. Excuse me?
Should be mapping from 0 to 1 closer to R for F inverse?
I'm sorry, say that a little bit louder because it's a little hard to hear.
This one, right?
No, because this is the inverse. F, oh, yes, you're right. It is correct. You're right, and I'm wrong. Thank you. And that works because u's are uniformly distributed on 0, 1 with probability 1. Actually, in this case, they're not even just with probability 1. They're just uniformly because I constructed them, so there's no problem, okay? So now, okay? So now I can construct sequences of independent, identically distributed random variables. Now I can even generalize this, where if inverse becomes a multidimensional F inverse, and I can generate, if you give me a cumulative distribution, which is defined on a multidimensional space, but they're not independent, I can construct the inverse like I did in problem 2, and I can generate the multidimensional random distribution with any distribution, okay? There's also a little detail associated with when you go to infinity. We'll ignore that. For the finite case, it's all straightforward, okay? Fine. So do you understand what a random variable is now? The random variable is not the thing that you get in your program, in your MATLAB program. That's a pseudo-random variable. Actually, if I flip a coin, the outcome of the coin flip is not a random variable. It's a physical event. It's the same thing. Pizzas are not random variables. Physical events are not random variables. This is not 2. This is not 2. 2 is an abstract concept that exists, in my opinion, independently of the physical world, okay? Math and the world are different. One could argue about, like, if the universe exploded, would the laws of logic still exist? And people can argue over such matters, although it's not going to matter to me. But over here is the math, and this is the world. The world and math are different. They are not the same. The connection between the world and math is a model or an analogy. That's why we have analog electronics. So random variables, the outcome of a coin flip is not a random variable. The signal in an electronic circuit is not a random variable. None of those things are random variables because those are physical properties of the world. A random variable is a purely mathematical concept, but we draw an analogy to the physical world, and we use that. We can only prove things about this side. So in the pseudo-random number generator in your MATLAB program, that's a physical world event, okay? It's not a random variable, but it has properties which are analogous. So, okay? So the reason, I ran out of time completely, but I do think it was important. So we're going to generate, so what is the goal? The goal is this. Generate random variables. Well, actually not, generate or / construct. I'm unclear about this, and everybody's unclear about it because it gets too confusing, okay? But you construct a random variable, you generate a pseudo-random variable, okay? So generate or construct a random variable, x with CDF f of x. That's our goal. And by the way, this can be multidimensional or it could be scalar. Let's start off with scalar because that's easier. Multidimensional is just actually relatively straightforward. It's not even an extension. We'll write it down as a scalar and everything will be true, okay? So, and you'd say, well, who cares? It seems pretty easy. We just do this, right? We just do that, correct? But what if if this thing is the distribution of a nuclear power plant, and we have to compute the inverse? I mean, it's just mind-bogglingly complex. No one can possibly do it. It's not mathematically, it's not computationally tractable. Even for scalars, it's not computationally tractable in most cases because, for instance, with a Gaussian distribution, you can't compute this because it's the so-called error function, which is a classic function that's like not tractable. So you'd have to discretize it on the interval, and then you'd say, well, how finely should I discretize it? Do I take 100 points like I'm doing a MATLAB plot? Do I take 1,000 points? Do I take 1,000,000 points? Do I take a Google of points? Okay? I don't know how to do it. So even then, even for a Gaussian random variable, okay? But you start getting the super complicated random variables, distributions, you don't know how to do this. So this is a general method for generating random variables from some specified distribution, cumulative distribution function, okay? So we're going to learn about two things. One is Metropolis, and one is Hastings Metropolis. In the Metropolis algorithm, you have this idea of you generate proposals and you accept or reject them. It's a lot like the whole academic endeavor, okay? Write proposals. The only thing that's missing are color graphics, okay? So you generate a proposal and you accept or reject it. It turns out that, I'll just write this, we came this far over, so I'll just say a few more minutes, why not? Okay, so your probability distribution can always be written in the form, well, always meaning sometimes. This is a different U, by the way. Shoot. I'll call it E. Oh, this is going to be a mess. I'll have to call it U. I'll figure it out later. U of x, okay? Right? That's the energy. Okay? So you have a state x, and you propose that it, so you have x, and you propose that x goes to x, say, plus w, or x prime, okay? Then you make the proposal, and then you say, if u of x prime is less than or equal to u of x, then I'm going to do like Python notation. Then then what you do is you make x goes to x prime. So you adopt the change. If x prime is greater than u of x, then what do you do, okay? If x prime is greater than u of x, you generate uniform random variable, okay? That's where everything I spent the first part of the class being the first 50 minutes of the class talking about. We know how to generate a uniform random variable in the interval 0, 1 now, right? And then what you do is you take with if u is less than e exponential of minus, this is crazy, u of x prime minus u of x, then so if it's actually, if u is, right, then you make x go to x prime. That's the pseudocode. So if the energy goes down, you accept the proposal. If the energy goes up, you accept the proposal with probability e to the minus the change in the energy. So if the energy goes up a lot, it's very unlikely you're going to accept the proposal. It's like, it's as if you have a proposal. You go, this is the amount of money that the proposal costs, if the thing costs, okay? So if somebody comes to you and you say, I propose to do this, it'll save you $10. They go, sure, okay? If you go, I propose to do this, it's not going to cost anything, sure, okay? It's going to cost you $10. Oh, well, I look at the proposal and I accept it with probability e to the minus the cost, okay? So if I come to you and I say, I got a proposal, it's only going to cost $10 million. I'm a nano guy, so I'm doing it cheap. And you go, no, forget it. It's a waste of time, okay? You get it? But it's important that you make a distinction between what the random variables are in your mind. So this has a concept in terms of basically being a purely mathematical statement, and also a statement about how to write your code. Okay? We'll go over it next time. Thanks a lot. I'll see you on a week from this Monday, okay? All right, bye. Was this helpful? Because I feel like the students don't have any idea what a random variable is. Because I mean, I know I was very confused about when I was a student. Like, I'm like, what is this thing, and why are you? And you know, they kind of sweep the whole thing under the rug with all this talk about a realization, as if that fixes something. It's they go, oh, it's a realization of a random variable. Like, what the heck does that mean? That's just gobbledygook speak for, I don't want to really tell you what I'm talking about, okay?
How do you decide what to propose?
Excuse me?
How do you decide what to propose?
Ah, very good question. Well, the problem is this. If you're very cautious and you make very, very incremental proposals, then you'll get them accepted a lot, but it won't make much change. If you make very aggressive proposals, then they'll just get rejected all the time. So the trick is to write a proposal that's just aggressive enough, but not too aggressive, right? So and then if you do that, then this generates an ergodic Markov chain, which converges more rapidly. So all ergodic Markov chains converge to their asymptotic distribution. That's what it means. But some converge much faster than others. Because what ends up happening is that you have this matrix P, right? You have this matrix P in the transition probability, right? So what will end up happening is if you look at the eigenvalues of P, right? You'll have one of the eigenvalues is always 1. But then the next largest eigenvalue might be lambda 2, right? If lambda 2 is extremely close to 1, then what ends up happening is that you have lambda 2 to the n. As you take higher and higher powers of lambda, the other transient modes decay slowly. And this lambda 2 could be equal to 1 minus 10 to the minus 10 to the 10 to the 10 to the 10, okay? Right? So what would happen is that it's going to converge, but you got to wait a long, long time, okay? Like maybe, a googolplex times the length of the universe or something. So it's a purely theoretical result in that sense. So, but then we have the Metropolis Hastings. Now, the other thing is that it's going to turn out there's a constraint on these proposals, which that they have to meet, which is a symmetry constraint. And in practice, that could be very hard to construct practically. So there's a thing called the Hastings Metropolis, which allows you to do it even when the proposals don't have the symmetry property. So this is the more practical method you usually use. But this is the method people first discovered, and it's the simplest one. In both cases, they're reversible Markov chains. And that's why I taught about reversible Markov chains. Okay? Read the notes here, because I think it will be helpful. But hopefully, I just felt, for whatever reason, it was important that you know what a random variable is.